Okay, great. Thank you very much. What I'd like to do today is I'd like to show you an innovation that is not really novel for the University of Wisconsin or me and my co-teachers, but it's a work in progress. It's being done on a large scale, and we have some measurements of real results. And I'd like to use this to illustrate some of the challenges and barriers that one faces when trying to create a new type of course. My collaborator throughout this work has been Ned Seibert. We started this about 3 years ago now. And the drivers for the design of this general chemistry course, so this is a first semester general chemistry course, are listed here. Some of these are institutional. It's been noticed in the university that there are a variety of achievement gaps. And for the context of this particular talk, an achievement gap will be whereby all other metrics, say ACT scores, math ability, etc., certain groups of students are achieving grades that are lower than expected. Those students are often underrepresented minorities. They might be first-generation students. There are, in some cases, gender gaps. And these have been identified by the university as a challenge, particularly because these achievement gaps are often found in gateway courses, courses that students have to take in order to go into their major, like chemistry, like calculus, like physics, like psychology. A common theme seems to be that courses that have a large amount of quantitative content are associated with achievement gaps. There are many people that are skeptical, too, because it's also been noted that these achievement gaps are more prominent in courses which use the full range of the grade scale. That is, courses that don't have averages of AB. We wanted to address the achievement gap, but we also have a problem in freshman chemistry, particularly in the first semester, that's a logistic problem. The logistic problem is that general chemistry, as I'll show you in detail, is growing rapidly at the University of Wisconsin. And our general chemistry program is designed as, for the most part, a 2-semester sequence, though we do have a 1-semester sequence as well. And that means that if a student starts the first semester, but then chooses not to take the second semester and abandon science, that means we've created a bottleneck in the system because there were a lot of students that wanted to take that first semester course that couldn't get in. And so we have logistical problems that arise from students that don't successfully complete, particularly the first semester course in a sequence. And so what we'd like to do as scientists, though, is we'd like students to continue to have interest in science, and we'd like to have them choosing to take the second semester of chemistry because they realize that sciences and chemistry are important to their world. Of course, we all want students to increase their mastery of fundamental chemistry concepts. And something that I think we often give short shrift to, that I think Jim really just mentioned, is that as an instructor, it's important that you find ways to keep teaching exciting for you, that it's fun to come into the classroom and teach, and that we don't end up slitting our throats. So the history behind some of the projects that Ned and I have carried out in the last couple of years, shown here from the NSF chemistry initiatives in the mid-90s. There was a New Traditions curriculum reform project. I was a co-PI with John Moore. In the UW system, in Oshkosh campus, the achievement gap was first noticed as a problem, and the data were presented. This achievement gap was demonstrated at the UW-Madison campus, so it's seen now on all campuses. And Aaron Brower, who was then the Vice Provost for Teaching and Learning, invited chemistry faculty, in particular Ned and I, to consider reforms that might address the achievement gap. So this was what we were really set out to try and address at the beginning. Here's a few graphical illustrations of what I mean by the achievement gap. If you look at the percent adverse outcomes, and that is getting a D, an F, or dropping out of a class is an adverse outcome. As a function of the students' ACT scores, you can see that, of course, the adverse outcomes decrease as the ACT scores increase. But the two lines shown here are for targeted minorities and then for non-targeted minorities. And you can see there's a consistent gap between the achievements in terms of adverse outcomes between these minority groups and the rest of the university. Another way of plotting this is to look at the magnitude of the achievement gap. Here we're plotting adverse outcome rate for non-targeted students versus targeted minorities. This is the line that we would have if there was no difference between the groups. And you can see that there's a large number of courses for which students are underachieving, the average being somewhere around here. Here's Math 221, which is one of our calculus courses. Chemistry 103 is, I think, this dot right here. And one final illustration of the achievement gap is in general chemistry courses, looking at, we typically have enrollments in this chemistry 103 class of about 2,000 students per year. If one plots, again, the ACT math score versus the average course grade point, then you find these correlations with the targeted groups falling below the non-targeted groups. So our charge was to try and address this problem. I don't want to give you all the story now, but I'll show you we failed miserably and with respect to this particular goal. All right, so over the past 20 years, there's been a large increase in enrollment, and it's particularly increasing rapidly now. Next year, the enrollment figures will go up from this by another 400 students. So we have a lot of students taking chemistry. We have a lot of demand on our laboratory spaces and on our instructor resources. From these achievement gap studies, what we find is that targeted minority students are twice as likely to have D's, F's, or drops than other students, given the same ACT composite. And this is especially a problem, as I mentioned before, in these intro and gateway courses. And so the Vice Provost for Teaching and Learning brought 5 departments together and asked people to try and create programs in their classes that could address these achievement gaps. And the idea was to make not just adjustments to the experience for underrepresented minorities, but to change the entire class under the philosophy that a rising tide will raise all boats. And so what we have done is we've decided to design our changes based on what we would call the 5 best teaching practices. And as has been mentioned earlier today, there's a lot of literature out there on practices that influence student success in college courses. I'd like to distill these down to the 5 best practices of teaching that are listed here. As Jim has just described to us, learning in context is a powerful way of getting students interested in the material and also, we hope, retaining the material. Education research tells us that cooperative learning techniques help students learn, and they help students over broad categories of different minority classifications, first generation versus non-first generation students. Unsurprisingly to us, but often not addressed, is that increased time on task increases success in courses. That it really does make a difference if you do homework, if you come to lecture, if you have lots of opportunities to exercise the knowledge that you're gaining. Increased frequency of feedback. Some students don't understand how well they're doing in a class, and we need to make sure that we give them feedback so that they understand when they're failing, when they're not failing. And the final best practice that we've focused on is maintaining a positive classroom climate. We've done this primarily by having a lot of cooperative learning, active learning activities in both the lectures and also in discussion sections. All right, so there are many ways that one can change the way they teach. These instructional degrees of freedom include things that we've heard a lot about already, using concept tests and clicker questions in lectures can be ways to make a lecture section much more interactive. Online homework and online tutorials and online video and simulation is becoming more and more important, and the quality of the materials that are available, even from publishers, is gotten higher and higher. A variety of group learning techniques, peer-led teaching, POGL, are also available. Peer review, having written assignments where students grade other students, and they're actually graded on their grading, are important tools that are becoming more and more accessible, primarily due to people like Orville Chapman. We've heard a lot about what I would call contextual learning or thematic learning, and I think we drew a lot of inspiration from the modular chemistry consortium that Angie Stacy was involved in with a large number of other people, including Jim Spencer, et cetera. We've made some use of spiral curricula in our innovations, where spiral curricula are based on the idea that one can introduce concepts at a fairly superficial level, but a lot of them early on. In fact, it's necessary if you're going to use real-world problems, big problems, that you introduce a lot of chemistry concepts early in the course in order to address those. But then what we'd like to do is to keep returning to those concepts and developing them with greater depth as we go through the semester. And so we've done some of this. And then, more popular now is flipping the classroom, having short video lessons that students may see before, and then focusing more of the lecture time on group problem solving and other activities. So those are the palette of things that we can choose from. And we've chosen a number of these. But our primary foci were to promote active learning in these large lecture sections. I should mention these are 350 student lectures. And so we promote active learning by lots of use of in-class questions. We now use clickers. We didn't when we started. During a lecture period, you typically find if you were to walk in a lecture, you have more probability of hearing all the students talking to one another than you have of hearing the lecturer talk. Because what the lecture really is doing is helping students go from one set of problems to another set of problems to another set of problems. We have discussion sections. We have 2 of them in our general chemistry classes. And the experience that students have in the discussion sections varies wildly with the TAs that they have. And we wanted to normalize this more, so we created a large number of inquiry-based cooperative activities that students were spending about half their time in discussion section working on. We require online homework and we require online tutorials to be done before the lecture, so students have some familiarity with the very fundamental concepts and calculations before they go into lecture. We make regular use of what we call challenge problems. These are group-oriented problems. They're turned in for credit, but the students are asked to work in groups. They're asked to identify who they work with. They typically have a week to work on each of these. There might be 4 or 5 during the course of a semester. And we also have workshop sessions in the evening where students can come and work together with a TA present who can ask some limited or can answer a limited set of types of questions. But it's a very cooperative learning, rich experience for the students. And we've also carried out some experiments with social psychological interventions, which if I have enough time, I'll describe for you. Okay, so the scope of the study, it's been ramping up slowly. We had our biggest year in the fall of 2010 where we involved 3 different lecture sections that were the course reform sections, 3 sections which were taught in what I'll call a more traditional way. They didn't have online homework. They didn't have concept tests and clicker questions and challenge problems. It doesn't necessarily mean that all the instructors were the same in those classes. Overall, we've had a treatment now, after last semester, I haven't updated this, but about 2,500 students have been affected by the reforms and about an equal number of students in the control section. All right. The hard part is, how are we going to assess what kind of changes that we're bringing about by incorporating all these techniques into our general chemistry class? So what we've chosen as our assessment elements are, one is grades and retention in the class. Unfortunately, we don't have data compiled yet. It's available for how many of the students would go on to take the second semester of chemistry, which is an important feature for us. We have common questions on the final exams between the control and the experimental sections. These are not taken from the ACS standardized exam, but about 15 years ago, the Exams Institute created a special exam for the New Traditions Project, and we own that, and we use some of those questions in this assessment. We do have one common essay question, and we also do a lot of student surveys, surveying things like hours spent out of classroom in the course, their perceptions of the course, using the class tools and the self-SALG, or student assessment of learning gains. And then, of course, the achievement gap is the other thing that we're monitoring during the course of this study. I can tell you in short that with all these reforms, and this was a lot of work for Ned and I to incorporate all these changes to the general chemistry class, we didn't affect the achievement gap at all for targeted students. Now, we didn't hurt it, so that's the good news, I guess. So we haven't done any harm. The fraction of adverse outcomes was essentially the same. If we look at performance on these common questions, which are multiple choice type questions, which are similar to ACS standardized exam questions, we don't see any difference between the sections. We've only done this once with a common essay question, and in our common essay question, we didn't see any difference at all. So this is discouraging, but I think there are some issues that are brought up from this study and some signs of encouragement. First of all, as I mentioned, there was no difference between the reform and traditional sections in our common questions. And the common questions, half of them are conceptual in nature, and half of them are more algorithmic in nature. And there's really no difference that's significant in the performance. However, there are some small differences between student responses to questions about things like their ability to think of molecules or reactions on an atomic level. So there are some small differences achieved with this new kind of teaching. Where we do see changes, students' perceptions change a lot. So the students, though they're not told that only their sections are involved in highly cooperative learning activities, perceive that they have many more opportunities to talk with other people and learn from other people in the course. They also can perceive that there's a stronger emphasis on conceptual learning in the reform section. Doesn't necessarily mean they do better on the exam questions, but at least they are indicating that they can see that there's a difference when we compare them with the traditional students. In terms of working out of the classroom, the 2 bars here are for reform and non-reform students, and we're asking now, did the students work with classmates outside of class to prepare for assignments or to study. And you see there are big differences in the reform section in the number of students that engage in interaction with their peers in doing classwork that carries over to more general discussion. So, for example, did they discuss ideas from chemistry with their parents, with their friends outside of class? And there are substantial differences between the reform and the traditional sections. So they're seeing some of a broader context of chemistry and talking about it with their peers. We also asked if they are relating chemistry concepts more to their daily lives as a result of this. And the statistics here are a little bit complicated to read, but there are small differences where the students in the reform section are more likely to agree that they see how chemistry is related to their everyday life than in the other sections. As I mentioned before, though, the reform did not affect the achievement gap for targeted students. It didn't affect fraction of adverse outcomes, performance on some common questions. I think one of our problems, and this is a general problem that we all face, is that as instructors, especially anecdotally when we talk with the students, we can see and hear big differences in the ability of students to communicate chemistry ideas and to relate it to everyday life, but we never measure that in our exams. And I'd like to point out a study that was carried out as part of the New Traditions Project about 15 years ago by John Wright and others, which is trying to really get at when you have this very active learning-oriented class and you don't see changes in exam performances, is there value added in other ways? And so the design of this study was really very careful. And what was done is there were two lecture sections of a different track, a more advanced track of general chemistry. Same size track, 100 students or so in each one, using a very active learning model and one a more traditional model. The grade distributions were the same. The instructor ratings by the students were virtually identical. The sizes of the class. And then the important part of this is that in order to assess this, we had 25 independent assessors, many of them from outside of chemistry in disciplines that require general chemistry in order for students to take courses in their majors. And these 25 assessors gave 30-minute oral exams to students, one at a time. They did 8 students each, so they're spending about 44 hours each doing oral exams. And they did these such that each assessor tested 4 students from the reform section and 4 students from the traditional section. And all the students that they saw from the 2 sections were paired in terms of grades in the course. So they have A students in, say, both courses, or B students in both courses. And the assessors were then asked to force rank all of the students. They had no idea which student comes from what course. They're asked to force rank then the 8 students that they evaluated. And what they found is almost uniformly that the students that were in the active learning class were assessed as being better performing in the oral exam than the students in the traditional class. So these are the bars pointing up are the cases where the students in the active learning course, and this is by assessor over here. These are the cases where the active learning students are doing better. These are the cases where the traditional students are doing better. So I think one of the problems that we are facing right now is we know that we put a lot of effort into reforms. We see some gains anecdotally, but we don't have good ways of measuring it. And so I'd like to put that as a challenge for others to look at. I'd like to just briefly mention, how are we on time? 5 minutes? Okay. including questions. Okay. I think what I can say is that many of you may have noticed a study that came out of the University of Colorado in physics, in which social psychological interventions, as simple as writing 2 15-minute essays on the importance of the material to you in the course, could give rise to big changes, in this case, in an achievement gap associated with gender. So the Miyake study showed, and so in this study, published in Science 2 years ago, it was shown that the gender gap in a second or third year physics class disappeared in the course of writing 2 15-minute essays on values of the students that are important to them and related to the course. The control study, the control group wrote about values that might be important to someone else. So that's the study. It's a very simple one to do. There's another kind of social psychological intervention called utility value, which is a similar sort of intervention, but focuses much more specifically on the material being taught in the course. So following the Karakata study and the Miyake et al. Study, we set up a fairly complex grid of values affirmation exercises where they're writing these 15-minute essays, and also analogous short essays that follow the utility value paradigm. And we've done this for a large number of students. And what we find is that, unlike Miyake reported in Science, there's absolutely no difference at all having either of these social psychological interventions. So in conclusion, we have tried to adapt our course to using the 5 best teaching practices. We do not find significant effects on achievement gaps or on assessments based on common exam questions. We do find that it does influence the students' attendance. I forgot to show the slide, but attendance in these classes is typically greater than 90% in the lecture, where it's typically less than 70% in the traditional. So students are coming, they're spending more time on the course, their attitudes are changing a little bit. We think value is added, but we just aren't capturing it in our standardized assessments. And so with that, I'd like to thank my coworkers, Ned Seibert, Aaron Brower, and Shisako Horibe, and I'd like to thank you for your attention.